pleasure to be here. And there are 3 changes with respect to the previous, well, at least 3 changes with respect to the previous talk. I have no videos. I'm not in space. We are now going underground. And from the future, we go now into history. The Large Hadron Collider is really a project of unimaginable complexity. And I must say, it's particle physics and engineering at its best. And I'm excuse myself here that I put particle physics in the front, because I was a particle physicist. So what is our scientific challenge? It is to understand the very first moments of our universe after the Big Bang. At the Big Bang, when it was tremendously hot, tremendously energetic, and tremendously small, and now expanding over roughly 14 billion years to today's size of 10 to the 28 centimeters. At that time, cooling down to 1.9 Kelvin, 1.9 degrees above absolute zero. That's the temperature of the outer space. Now, how can you understand the very first moments of our universe? Well, you can use astroparticle physics or astrophysics. And they use telescopes, and with these telescopes, they look into the history of the universe. And when you look into the history of the universe, you do it usually with photons, with light particles, but then you are running against a wall. And this wall is around roughly 380,000 years. Because in the first 380,000 years, the universe was still so hot that no stable matter could be formed, and the photons which appeared were immediately eaten up again, so no information could get out. It's already not so bad to get 380,000 years close to the Big Bang. But with particle physics, you can do it differently. We are using microscopes and not telescopes, and not to look into the history, but to reproduce the conditions of the early universe. So that's a big difference, microscopes and reproduction. So the Large Hadron Collider project is a super microscope with 4 huge eyes. It is the highest energy accelerator in the world, well, on the Earth, with 4 huge detectors. And we are getting closest to the Big Bang, namely less than 10 to the minus 12 seconds, or for the non-scientists, as close as 1/millionth of a millionth of a second, breaking in that way the wall of this hidden universe. Nobody else gets closer. So this Large Hadron Collider project, you see here, is in a very nice landscape. You see the Lake Geneva, but it's underground, roughly 100 meters underground. It's the largest scientific instrument ever built. It's a particle accelerator of 27 kilometers circumference, some 100 meters underground. It collides protons to reproduce the conditions a millionth of a second after the birth of the universe. And we do that 40 million times a second. And what happens in these collisions, we register in 4 huge experiments. This is a huge challenge. To design and to construct such a project, many thousands, many more than 10,000 technicians, engineers, and physicists from all over the world, it's an international cooperation, from all over the world, and from many different disciplines, had to develop new technologies, had to develop new engineering aspects and concepts, and they had to work together over decades. More than 30 years ago, the first paper on that project appeared. So this is several decades these guys have to work together. The question is, can that work? Well, you know the answer, okay. In order to do that, we need the fastest racetrack on the planet. Trillions of protons are bunched in up to 2,808 packets and race around the 27-kilometer ring in opposite directions, over 11,000 times a second, traveling at, you can read it yourself, % of the speed of light. And they need to be kept on their track by more than 1,200 superconducting dipole magnets, which keep the protons on track. These magnets are 15 meters long, more than 8 Tesla magnetic field. And they did not exist when the project was launched. They had to be developed. They are constructed from the superconducting niobium cable, and the combined strands of these 1,200 magnets would go around the equator roughly 9 times. Now roughly 7 times. I need glasses in principle too. The filaments of the strands would stretch to the sun and back 5 times. It took years to develop and to build these things. And in order to do that, to run them, we need to create one of the coldest places in the universe. Because we have an operating temperature of these magnets of about minus 271 degrees Celsius, which is just 1.9 degrees above absolute zero. And now I realize the outer space is not 1.9, this is 1.9, the outer space is 2.7. Sorry, that was my mistake before. The LHC is colder than outer space because outer space is 2.7. And in order to cool the magnets down to this temperature, we use superfluid helium to cool them down. It's the most efficient cooling with a superfluid helium. However, that creates a big challenge. And the cryogenic challenge for this world largest 1.9 Kelvin cryogenics installation is that approximately 80 tons of superfluid helium must be maintained at this 1.9 Kelvin during the entire period of operation. The mass cooled by the helium is 30,000 tons, and just pre-cooling this mass uses 10,000 tons of liquid nitrogen. Small amounts. But why do we need so much? Because the surface area cooled exceeds 40,000 square meters. And superfluid helium creeps through all cracks. So all leaks of non-viscous superfluid helium had to be eliminated after tens of thousands of welds, because otherwise you lose your helium. That's a disaster. And then you need to have an efficiency that allows a 0.1 Kelvin, a 0.1 degree gradient over an octant, 1/8 of this 27 kilometers, over an octant of 3.3 kilometers to be achieved. So not more than 0.1 Kelvin temperature difference over 3.3 kilometers. And then, of course, you need high-precision temperature sensors and instruments which have to function in a very hostile radiative environment that's similar to outer space. Just to show it to you, 123,000 helium-tight in situ welds. And some of these guys had to be very slim in order to do the welding. Well, you can move, okay. Total intermagnet connections, 1,700. High current splices, 10,000. And if people remember that something went wrong in the year 2008, one of the 10,000 blew up. And 1 in 10,000 is a tenth of a per mil. So you have to be much, much better. Yeah? So you have to be extremely good. Soldering and welding in difficult conditions, I showed it to you, but very high quality needed, and 250,000 welds in the tunnel environment. This is a mega engineering project. And this is only part of it. In order to keep the protons, we have to create one of the emptiest places in the solar system. You see here, these are 2 vacuum tubes in which the protons run clockwise and anti-clockwise. And to accelerate the protons and to keep them circulating for many hours, 24 hours or so, requires a vacuum as empty as interplanetary space. The pressure of the LHC vacuum is around 10 times lower than the atmosphere on the Moon, the pressure of the atmosphere on the Moon. So, these are already fantastic challenges. But then you have to capture the beam of trillions of protons, you have to accelerate them, and you have to hold them. So as I said, up to 2,808 packets of protons. They are like pencils of sub-millimeter width of the pencil, which travel at a distance of 7.5 meters, one behind the other. And in each of these packets, there are over 10 to the 11 protons, over 100 billion protons. And they travel with a speed close to the speed of light. And during the acceleration from the injection energy up to the final energy of the collision, the energy of each beam has to increase by approximately 300 megajoule within 20 minutes. And during that time, the protons travel a distance further than the round trip to the sun. So we are a bit faster than SpaceX. But underground. Now, the energy stored in these two beams is 720 megajoule. Now, you have to remember 700 megajoule melt 1 ton of copper. And you dissipate that in 88 microseconds, then you lose the whole beam. And that would produce an 8 terawatt energy, more than the electrical capacity installed in the world, or 90 kilograms of TNT per beam. It's obvious you should better not lose the beam uncontrolled. Because then you start the whole project again. So, what do you need then? You need finely controlled feedback loops to maintain position and stability of the packets of protons to a high precision. And the engineers have developed, and physicists and engineers together have developed sensors to precisely determine the position of each of these packets in space as they speed through the LHC. In addition, you are in a very harsh radiation environment. All the complex equipment must remain working faultlessly for many hours at a time. Again, another fantastic challenge. And don't forget, there's also energy stored in the magnet system, not only in the beam, also in the magnet system, and that corresponds to roughly 10 gigajoule. 10 gigajoule corresponds to an Airbus 380, flying with 700 kilometers per hour, or an aircraft carrier traveling with 55 kilometers per hour. Again, these are huge numbers which you have to control and which you have to unload. When there is a problem in the machine, you have to discharge the magnets very, very quickly in order to be efficient and in order to have not any accident in the machine. Suppose we can do that, then it looks like this. This is when I was still Director General of CERN. This is the way I wanted to see the LHC. Nobody in the tunnel. All the magnets closed. We can start running the machine. So now we have mastered all these engineering challenges for the accelerator. But the accelerator without detectors, without eyes, is nothing, except for the accelerator physicists who want that, because experiments only disturb them. Okay, so the accelerator is ready to go. But now we want to do physics with these beams. Okay, so we need the eyes. So what do we do? Here you have the accelerator on the top. You have clockwise and anti-clockwise the bunches of the packets of the protons. And then these protons you bring to collision. And you do that, of course, in this small, very small vacuum tube. In order to have effective collisions, you have to imagine that we do the same as if you would, from your east coast, throw a packet of knitting needles towards Europe. We, at the same time, throw a packet of knitting needles from Europe towards the US. And they have to collide above the Atlantic. That's what we are doing here. However, on a much smaller scale. Now, if we achieve to collide the protons, then who is interacting are not only the protons, interacting are the quarks and the gluons, the constituents of the protons. And out of this interaction, there's a production and decay of many, many new particles. And this we want to register and we want to analyze. And this is why we have to detect what happened in these collisions. That means we need eyes, huge eyes, we need huge experiments in order to detect what happened in the collisions. So what we deal now with the hottest spots in the galaxy. So we are the coldest part and the coldest installation on Earth, but we have the hottest spots in the galaxy. Because when the two beams of the protons collide, they create temperatures much, much higher, 1,000 million times hotter than in the heart of the sun. However, in a minuscule space, the energy of the protons is not the key, it's the energy density. That means the energy divided by the size of the proton. And the proton size is extremely small, so the energy density is extremely high, and that produces these hot temperatures. And this brings us so close to the birth of the universe. So it's the energy density. And when we started in 2009, we started with the LHC, a new era in fundamental science. And we had 4 huge detectors which register, or we still have 4 huge detectors which register what happens in these collisions. And you see them here. You have CMS, Atlas, the 2 largest ones. This one is the biggest one, LHCb and ALICE. And all do different physics. All are complementary, but all have also overlapping interests. So one experiment can cross-check the others. And that's very, very important. So these experiments are sitting in large underground caverns, up to 100-meter underground. And these caverns are up to 53 meters long, 35 meters high, so it's like a 10-story building, 30 meters wide. They had to evacuate 300,000, excavate 300,000 tons of rock, and then afterwards again use 50,000 tons of concrete. Just to give you an example, this is one of the surface areas of one of the experiment sites. And you see it is nearly finished. This is the access shaft where you bring down the experimental pieces, and then you have a lot of surface halls. So it's also civil engineering at its best. Especially this cavern had a problem that they had to they had to freeze before the concrete part. They had to freeze the whole 100 meters because there was water coming in. So you had to freeze the shaft, then put the concrete on, and then you had a stable situation. And then you have this cavern. Once it's ready, it looks like this. And this is at the beginning, before it was filled. And now you have to fill it with huge detectors. And you have to imagine that the whole thing here is essentially filled with a tremendous amount of sensors, of experimental equipment, in order to measure what happens at the collisions. The biggest detector is the so-called Atlas detector. It is 46 meters long, 25 meters diameter, 7,000 tons, so it's not very, very heavy. So with this size, it would even swim. It has around 100 million sensors, 100 million channels, needs 3,000 kilometers of cables. And the toroid, which you see here, they have a stored energy of 1 gigajoule and use a current of more than 20 kiloamps. And of course, it was assembled in the cavern itself, because these huge pieces you can only bring down in single ones, individually. So this is when all the toroids were installed. And this is really heavy engineering, industrial engineering at its best, but dealing with delicate pieces from around the world, which then have to be fitted with millimeter precision, because you don't want holes. You want everything covered by installation. And then to arrive at the final detector, people with good eyes can now see that there are still pieces of the toroids visible here. So this is the end cap which is being moved to close in this wall here, and then the detector is finished, is complete. The whole volume of the cavern essentially is now filled with some 100 million sensors of many different kinds, which were developed in over 40 countries by over 3,000 physicists and engineers. And within the whole volume of this detector, you arrive at an average measurement accuracy of roughly 0.1 millimeter over the entire volume. On the inside, it's much better. On the outside, it's worse. But you have to appreciate that. This is nearly 50 times 25 cubic meters, and everywhere in that volume you measure with 0.1 millimeter accuracy. Okay. The other big experiment is the CMS experiment, which, as well as Atlas, has around 3,000 members, again from around 40 countries. And you see here the beauty of this experiment, which you might be able to appreciate. The persons here look much bigger because the C in CMS stands for compact. But it's still 21 meter long, 15 meter diameter, and it is much heavier than Atlas. It weighs 12,500 tons, more than the Eiffel Tower, which has 7,500 tons. It uses the largest superconducting solenoid ever built, field of 4 Tesla, 6 meter diameter, 12 meter length, 2.5 gigajoule stored energy. So there's a tremendous amount of energy also stored in these experiments. It has the largest semiconductor detector, the largest silicon detector in the world. Surface area of the silicon is more than 200 square meters and has alone 75 million electronic channels. It took years to develop it, and it will take years to upgrade it. And here you see on the left, it's the naked detector, and here you see when it's cabled up. And of course, cables are always disturbing because they use some space. But you need cables to read things out. The measurement accuracy of this silicon detector is around 0.01 millimeter. 10 micrometer is the accuracy. You want to measure the spot of the colliding protons with as much as possible accuracy. But there is also another aspect of engineering. And I like this aspect very much. And I think you, in your award speech, also mentioned that. And that's this. You know what that is? These are shells. Yeah? So these are over 1 million World War II brass shell casements from the Russian Navy, which was here in this case used to make pieces of the detector. Because it is a very, very, was ist rein? Pure, thank you. A very, very pure brass, which they needed in order to have the best possible detector part. And I think this is a much better use of this pure brass. Okay. So I think everybody liked this very much. And the workers don't look very, but okay. But CMS had another engineering challenge. CMS was assembled and tested above ground. You remember Atlas was assembled in the cavern. CMS was assembled and tested above ground. And then it was lowered into the 100-meter deep cavern in a few very heavy pieces. If I'm not mistaken, 6 pieces or 7? 6. Yeah, 6 pieces. And this one is the heaviest piece which arrived safely down in the pit after a 12-hour journey for these 100 meters. It was a 2,000-ton piece, so they needed the strongest crane in the world. It was a company that had this crane, a 2,500-ton crane, which also constructed the walkway between the Kuala Lumpur Twin Towers, and they also built a stadium in Durban, South Africa. So you see, everything comes together. Fine mechanics, fine engineering, and heavy engineering. And it's beautiful forefront engineering. Yeah? I like this photo. It's like arts. So now we have constructed the accelerator, and we have constructed the detectors. What's next? Well, physics. Now we want to do physics. Okay, so the protons, they collide inside this tiny tube in the heart of the detector. Can this work? Well, 1 billion pairs of protons interact per second. And in these interactions, in these collisions, hundreds of billions of particles are produced every second. I think you agree this is a very harsh environment in which you have to measure and register. And we are looking for physics signals which are 10 to 11 orders of magnitude below the rate of all signals together. So you have to find one thing out of 10 to the 10, 10 to the 11. And to give you a comparison, the number of human beings is roughly 10 to the 10. So the LHC detector's job is like trying to find one person in all of humanity who meets a special set of criteria. Okay? And not only once, you need to do it several times, many times, in order to have enough statistics. And it works. It really works. And imagine 3,000 scientists working on that. 3,000 egos. Yeah, and it still works, okay. As you see, and you know, the discovery was in 2012, which gave the Nobel Prize in Physics 2013 to these two gentlemen, François Englert, oops, I'm too excited still about that thing. François Englert and Peter Higgs, for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which was recently confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. And this is a key, is a milestone, because it explains, it tells you why you can exist. Because if these subatomic particles would be massless, no matter could exist. No, you could not form stable matter. You could not form matter. So now we have told you why you can exist. Huh? That's something. Now you know it since 4 years. Okay. So we still have a scientific program at the Large Hadron Collider until around 2035. That's our short-term planning for the next 20 years. And in 10 years, we will upgrade the accelerators and the experiments. And these upgrades present new engineering challenges. There are very many new challenges ahead of us. So, at the beginning, I told you to design and construct the LHC project. Many thousands of technicians, engineers, and physicists, again, from all over the world, from many different disciplines, had to develop new technologies, new engineering concepts, and they had to work peacefully together over decades. Yes. If science doesn't show that you can work peacefully together, nobody else can show it. That's my conviction. And we have shown that. And I must say, the LHC project is a marvel of engineering and science, and it works beautifully. And it fascinates the people. Thank you.